Hello. Am I audible?
Yes, sir.
Yes, Assalamu alaikum, sir.
All right. Okay,
Sir, how are you, sir?
Sir, audible, sir.
thank you. Yeah, I am improving. Now I can walk a little, but still, doctor asked me to not to walk too much for the stability. Maybe after this week, I can go to my office. Please offer dua for me.
Inshallah, sir.
Okay, thank you. I think we should start. Thanks everyone for joining the session. Now, today's session, we want to discuss one of the pioneer machine learning algorithm. It is called the support vector machine. So before the deep learning era, specifically the support vector machine is one of the pioneer. And in most of the cases, on that time we tried the support vector machine because this one was the pioneer. But still, the support vector machine in cooperation with other algorithms are also performed well. And there are many concepts in support vector machine. Those are also necessary to develop maybe some new algorithms. And the optimization method we will discuss here in this support vector machine, that is also applicable for many types of optimization, solving many types of optimization problems. And that's why learning support vector machine is necessary. As it is mentioned here, the part of this lecture is adapted from the lecture of Professor Leskovic of Stanford University. So before going to discuss about the support vector machine, we need to understand few terminologies. And we need to understand those terminologies very clearly. As in the definition, we can see the support vector machine is a supervised learning approach. Okay, that means supervised learning approach. So that means in our data set, we have to have the class levels, or you can say the annotated data. So support vector machine, we can think about the support vector machine if we have a data set, and on the data set the annotation is there or class level is there. And the support vector machine use the support vectors. Here it is mentioned about the support vectors for the classification and regression. So that means the same problem, same algorithm, the support vector machine. We can use this one for classification, solving the classification problem and solving the regression problem also. Usually call it support vector classifier and support vector regressor. The first terminology here is support vectors. Yeah, support vectors. Then at first we need to understand what are the support vectors. Support vectors are the data points that are closer to the hyperplane. So that means this is another terminology, hyperplane. So we need to understand the hyperplane. And then influence the position and orientation of the hyperplane also. That means the support vector, the data points from our data set, we have to select the sum of the data points. Those are closer to the hyperplane. Usually we call those are our support vectors. And these support vectors, it will influence the position and orientation of the hyperplane. The position and orientation of the hyperplane. That means based on the support vectors, the position of the hyperplane, it can change. Okay, the orientation can be changed. based on the support vectors. And another terminology here is using these support vectors, the margin is maximized by the classifier. Okay, so another terminology is margin. So we need to maximize the margin. Then we need to understand what is margin. The three special terminology: the support vectors, the hyperplane, and margin. So we need to understand these three terminologies very clearly to understand the support vectors. I think it's better if I can record the question. So to understand the support vector machine, we need to understand the support vectors, hyperplanes, and margin. At first, try to understand the support vectors. So as it is mentioned, support vectors are the data points that are closer to the hyperplane, closer to the hyperplane. So let's say we have a given data set. Let's say this is our data set. And we want to classify positives from the negatives. In this case, we can see in this data set, we have the data points. Let's say this is the data point A. This is our A. And this is B. And this is C. So three data points. Those are positives. And G, this is E, and this is F. So these are from the negative class. And using these data points, we want to train our model. Okay? We want to train our model. That means in our data set, the training set, we have 6 data points. 3 are positive and 3 are negatives. Then actually, we want to build a separator, or we need to find out a separator that can separate positives from the negatives. Okay? So that means, okay, maybe you can draw a separator like this way, and that can maybe separate positives from the negatives. Okay. Let's say now consider that the one-dimensional case. Let's say one-dimensional case. We have the data set. Let's say this is one-dimensional instead of 2, just one dimension. Let's say we have a few data points. Few data points are there, like and some other data points also we have. Let's say this is one-dimensional case. Just maybe consider the weight of few people. Okay? The weight of few people. The weight. The weight. So based on the weight, we can classify the people in 2 groups. Like one is maybe people with obesity and people with no obesity. Okay. Let's say we can see the weight of different people here. This is maybe 45 kilogram, and the weight of this person, the second subject we have, maybe you can see 50 kilogram, and this is 55 kilogram. And this is, maybe you can consider this is 75 kilogram or 65. Okay, so let's say this is 65, and this is 70. and this is 75 kilograms. So as the support vector machine is a supervised learning approach, so what we have to do, we have to know that means which of these subjects or which of these individuals are individual with obesity and which are not. So let's say these are the people. These are the people with obesity. Okay, these are the people with obesity that they have. They are obese. Okay, yes, they have the obesity. Okay? So that means let's say yes means positive, and these are the people with no obesity. Okay, so no obesity. No, they don't have the obesity. So this is considered that those are the negatives. Okay? Those are the negatives. Okay, if you want to build a model using this data set, and that can clearly identify, that is, what are the obese individuals and which are the not obese individuals. Then which are our obese individuals and which are our no obese individuals, people with no obesity. So for that case, if we train the model, then what it will do, it will try to, as this one is just one dimensional, so it will try to find out a threshold. So it will try to find out a threshold, and that threshold, maybe below that threshold, is the people with no obesity, and greater than the threshold is the people with obesity. So let's say the threshold, it will consider a threshold here. That is the threshold TH. This is the threshold, and the threshold is 57. So the model learned that if the model can consider 57 as the threshold, then below the threshold, that is 55, 50, and 45, those are the people with no obesity, and greater than threshold, the 57, greater than or equal 57. Okay, so those are our people with obesity. Okay, so that means 65, 70, and 75 are the people with obesity. Okay, people with obesity. So that means the learning algorithm will correctly identify each and every that is the subjects here. So that means we can get the 100% accuracy from that model. Okay, 100% accuracy. That means based on this threshold, 57. Based on this threshold, that is 57. Now consider a test case. Okay, a test case. We can consider a test case. Maybe the test case is here. Okay, one of the subject. This is our test case, and the weight of this subject is consider this is 58. 58. So based on our learned model, what will be the class level of this new individual? Based on our learned model, what will be the class of this new individual?
Obese.
Obese. Okay, that means it is greater than 57. 58 is greater than 57. So it will classify this individual as an obese people. So that means this people has the obesity. So it will classify like this way. Now someone asked that, okay, interpret why you are telling these people as an obese people. That is, we can say that we need to interpret the result or explain the result. For the explainability, maybe we can utilize several explainer. One of the explainer consider about the nearest neighbor. Okay, nearest, we want to explain the result based on the nearest neighbor. So nearest neighbor, or we can say the k nearest neighbor. K, consider that just one k nearest neighbor. Utilizing the k nearest neighbor, we want to explain it where the value of k is 1. So that means it will try to find out the most closest or most nearest subject of this test case. So this is our test case. So it will try to explain the answer of our model utilizing the k and n, the k nearest neighbor. So k nearest neighbor, considering the value of k is 1. The value of k is 1. So it will try to find out the nearest neighbor, just the nearest individual. The nearest individual, we can see that is the closest individual for this test case. It is actually the 55. So this one is nearest. And this one is nearest. Then it will try to explain that, okay, the test case here, it is positive, and the class level of the nearest people, is negative actually. So this is negative. These people has no obesity, but these people has the obesity. So if we can apply the KNN or k nearest neighbor to explain the answer, then our explanation will be wrong. Okay, that means it will not justify that. That is, these people has the obesity. So that means we can say it will fail to explain the answer, fail to explain the result. So that's why the problem is setting threshold. Okay, so that means our learning model set the threshold 57, but if it set the threshold 57, it will not explain many of the cases. So it will fail to explain any of the cases. So that's why can we set a better threshold? Okay, can we set a better threshold? Think about okay, we want to determine.
Sir, maybe in between the lower value of obesity and the higher value of not obese.
Yes, you're right. Actually, we need to select different methods like whatever you proposed. I think my computer screen is not visible. Okay, so we want to find out a better threshold. Okay, better threshold for that. How can we find a better threshold? So for that, from the training set, that means from the in our training set we have these 3 people and we have these 3 people, 3 obese people and 3 people with no obesity. And we need to find out, that means the people with the the, the highest weight of the people with no obesity. The highest weight of the people with no obesity is 55. The highest weight of the people with no obesity. So here is the 55. And the lowest weight of the people with obesity. So people with obesity, the lowest weight is 65. Okay, so this one, 65. So plus 65. That if we can divide it by 2, okay, so divide it by 2. So then it is 120 by 2 is 60. So this is 60. So that means we can set a threshold instead of 57. If we can set a threshold that is 60. Okay. Now, still in the training time, we can see if we set the threshold 60. In the training time, we will get the 100% accuracy. Okay, because we can say these 3 people's weight are less than 60, and these 3 people's weight are greater than 60. So still in training time, we will get maybe the 100% accuracy, but our threshold is changed now. So now a test case again, the previous test case we can consider. So this is our test case. The individual with weight 58 kilogram, and based on this threshold, 60, we can see 58 is less than 60. So if this one is less than 60, so we can say that these people has no obesity. Okay, so that means it will return the negative. Return the negative. Okay, and again, if we want to explain the answer, okay, if we want this explanation why these people has no obesity. Again, if we try to find out our there is explainer as Kn, and K is 1. So it will try to find out the nearest neighbor. So the nearest neighbor here is 55. Okay, 55 is nearest. The distance from 58 to 55 is just only 3. Okay, this is 3, and distance from 58 to 65 it is 7. Okay, so total 7. Distance is 7. Here to this is 7. So we can see the nearest neighbor is 55. And what's the class level of the nearest neighbor? The class level of nearest neighbor is negative. And the class level of the test case is also negative. So we can explain that, okay, actually, the most of the people from the test case, from the individual, is the people with no obesity. Okay, so that means the weight of the most of the people of the test case is those are the people actually with no obesity. So we can say that, so we can consider that, okay, these people has also no obesity. Okay, so that means this time we can explain it clearly based on our explainer. Here explainer is our K nearest neighbor. So we can consider that this threshold, this is this threshold, this one is better threshold than the previous one. Though if we consider 57, in training time we got the 100% accuracy. If we consider 60, we got the 100% accuracy. But we can see that in terms of explainability, the threshold 60 will provide us the better explainability. Then what does it mean? Actually, we can say that if we consider these 2 data points, this one and that one, we have to place the threshold at the middle. We have to place the threshold at the middle point. So that means here. So this one will be our better threshold. Okay, so we can consider this is actually what? This is our separator, okay? This is the separator threshold. It separates positives from the negatives, okay? Separates positive from the negatives. And the position of this threshold controlled by these two data points. So this one is one data point and this one is another data point. These two data points actually control the position of this threshold. So what does it mean? It means that if we consider about this is our separator threshold, then the position of these two is controlled. This threshold is controlled by these two data points. So these two data points we can consider as our support vectors here. So these are our support vectors. Support vectors. So why we call it vectors? Because each and every data point actually we can consider as the vector, okay? Vector, because in 1 dimension, 2 dimension, 3 dimension, whatever the dimension of our data set, we can represent each and every data point as a vector. So that's why you can say these are the two data points. We can consider those are our support vectors. And here is the threshold, okay? This is the threshold. We have to place the threshold at the middle between these two support vectors. And the middle point threshold is the beta threshold for explainability. Okay, now we have to consider our two-dimensional case. So that means we have already considered the one dimension, but now we want to consider the two-dimensional case. As we have the data set, so this is the data set. Is my computer's screen visible?
Yes, sir.
Okay.
No, sir. We're seeing the previous slide.
That's the previous slide. Okay, let me try to reconnect again. Okay, I think it's visible now.
Yes, sir.
Okay. So now consider that we have two-dimensional data points. So we can see not only the weight, but also height is given. In x-axis we have the weight, in y-axis we have the height. The weight and height is given. And now based on the height and weight, we want to define the obesity. And again, let's say A, B, and C. These are the three people. Those are maybe we can say obese people, and these are the negative. The people with that is the negative class. Those are our people with no obesity. And we want to separate the obese from no obese. And now we can see that that means for the two-dimensional case, if we just set a threshold, that will not be enough to classify or to separate positives from the negatives. Okay? So that means for two-dimensional case, a point or maybe a threshold is not enough to separate positives from the negative. So what we need a separator line. Okay, so this is the separator line. Separator line to separate positives from the negatives. And again, if we can consider, okay, we want to draw the line. So this is a line, maybe this is a separator line. And this separator line, like the threshold, we want to find out the support vectors here. Then what are the points we can consider? Those are our support vectors. So considering this separator line, we can see that the B is closer to the separator line, and also E is closer to the separator line. Okay? So these two data points, one from positive and one from negative, we can consider that this B and this E. So those are our support vectors. Okay, we can consider those are our support vectors here, B and E. Why? Because those are closer to the hyperplane. According to the definition, we can see support vectors are the data points that are closer to the hyperplane. Okay, so that's why we can consider those are our support vectors. And where we should place the this separator line? We should place the separator line at the middle between these 2 points. Between these 2 points. So maybe you can say we can consider this one, or maybe you can consider like this one, okay, or you can consider maybe that one. Okay, several separators we can draw for that case. Okay, those are our considering our support vectors. So that means these support vectors also control the position and orientation of our separator. Okay, separator here. This separator is our line. Now think about three-dimensional case. Okay, so think about three-dimensional case. The data points we have. If we consider the three-dimensional data. Okay, consider that now three-dimensional case. Okay, not only the weight and height, we have another dimension. Let's say another dimension is here. This is the gender. Okay, gender. Not only the weight, height, we also consider the gender to find out the obese people and no obese people. There is the people with obesity and people with no obesity. So now we have three-dimensional data point. Yeah? So that means each and every data point has 3 dimensions. There is X, Y, and Z. Now tell me, that is what kind of geometric object is necessary to separate positives from the negatives? Is it a threshold? Is it a line?
So we need planes here.
Okay. Yes, we need planes here. Yeah, we need the planes here to separate positives from the negatives. Maybe we need the planes here. Separate positives from negatives. So this is the case for the three-dimensional case. Think about one more dimension. Let's say we have 4-dimensional data. Another data point is here. We can consider about there is the BMI. So that means in our data set we have 4-dimensional data is given. There is height is given, weight is given, gender is given, and BMI is given, and then class level are also given. That means whether these people have the obesity or maybe no obesity, the positive and negative is given. Then again, we want to separate positives from the negatives. Then what kind of geometric object is necessary for that case? So we want to separate positives from the negatives. We have 4-dimensional data. Okay. So for the line equation, for the line, okay. So for the line, we can think about the equation of the line. That is a maybe x plus b y plus c equal 0. So this is equation of a line. So for the 2-dimensional data, we can maybe we need to find out a line like this: ax plus by plus c equals 0. Equation of a line. Okay. For the 3-dimensional case, we need to find out the plane. Okay. For that case, equation will be a x plus b y plus c g plus d equal 0. Yeah. So we need this kind of plane. Okay. So equation of a plane. Maybe this is the equation of the plane to separate positives from the negative. Then for more dimension, that means for 4-dimensional case, the equation could be a little bit different. Okay, it could be a little bit different, like a x plus b y plus c g plus d p plus p equal 0. This equation, okay, this equation actually more than 3-dimensional object, we call those objects are the hyperplane. Okay? Hyperplane. So this is equation of a hyperplane. Hyperplane. We know the plane equation. We know the line equation. So this is the equation of a hyperplane. So 4-dimensional, 5-dimensional, 6-dimensional, whatever the dimension we can consider. The geometric object we can think about, that is our the hyperplane. So this is the equation of the hyperplane. So now we want to form the generic form. We want to form, or we want to build a generic form of the hyperplane equation. So instead of x, y, z, b like this, because we can consider maybe the 1000 dimensional. So on that case, x, y, z, that's not useful, or that's not, I think, that's not the correct way to represent our equation. Instead of that, can we write the same thing? So this one is, instead of x, we can say this one is x1 plus b. Instead of y, we can consider this one is x2, and then c, instead of g, we can consider this one as x3, and then d, x4, and then maybe the constant is b equal 0. Okay, equal 0. So the same equation instead of x, y, z, we can write those are just x1, x2, x3, x4. Actually, x, y, z, b, those are our dimensions, or those are our features. Okay, so the x is weight, y is height, and capital G is maybe gender, and B is BMI, like this. Okay? So here that means the x1 is the first feature, x2 is our second feature, x3 is third feature, x4 is fourth feature, fourth dimension. Similarly, we can also write instead of just ABC, small ABC, we can consider A equal W1. So here is x1, and then B is our W2, x2. C is, we can consider our W3, x3. Then D, we can consider D is our W4, x4. B equals 0. Okay, we can consider this one. Okay, W1, x1, W2, x2, then W3, x3, W4, x4 plus B equals 0. Okay, so that means this is the equation of a hyperplane. Now we want to write the equation of the hyperplane in vector form. Okay, vector form. So if we want to write the vector form equation, then okay, consider that we have a vector that is W. For the weights, we have a vector that is called the W, and we have W1, W2, W3, and W4. So these are our vector W. Okay, and the feature vector, the X, we can consider. It has like the four features we have: the X1, X2, X3, and X4. These are our four features. Okay? So we have four features. Now we want to find out the W transpose X, the dot product of these two, that is W and X. We want to find a W transpose X. So it means W transpose. So W will be W1, W2, W3, and then W4, and X is X. So X will be X1, X2, X3, and X4. Yeah, so W transpose X. So if we multiply this W and X, so this vector, so here is the W1, and here is our X1. We can write it like this is W1, then X1 plus of W2, X2, then W3, X3 plus W4, X4. W4, X4. So W transpose X is our W1, X1, W2, X2, W3, X3, and W4, X4. So if we can see our hyperplane equation here, this is W1, X1, W2, X2, W3, X3, and W4, X4 plus B, plus B. So plus consider the W transpose X plus B. If we add the B here, then we have to add the B here. Okay, add B. So that means the hyperplane equation, we can write it as W transpose X plus B equal 0. So this is the equation of our hyperplane. So this is the generic form of our equation of the hyperplane. Okay? Generic form of equation of hyperplane. W transpose X plus B. So this is the generic form of our equation of the hyperplane. Now, okay, we got the equation of a hyperplane. So now you can consider like any dimensional data point, whatever the dimension is. It can be 5, 6 dimensions, 100 dimensions, 1000 dimensions. Then using this equation, we can find out the equation of the hyperplane. Okay? So that means it will have the dimension, and also it will have just the weight. Okay, so W, the coefficient of each and every dimension, that is weight. So this is the equation of generic form of the equation of hyperplane. Even if we consider that we have two-dimensional data, the two-dimensional data, it means we have just x1 and x2, two-dimensional data, like the weight and the height, okay? The two-dimensional data. Still, we can find out the equation for that. So it will be W transpose X. So we will have this 2W. So that means W1 and W2. After transpose, we will get this row vector. And then X is our, we have two dimensions only, that is X1 and X2. So the equation will be W1 X1 plus W2 X2, then plus of B equals 0. So here is B equals 0. This is the equation for our two-dimensional case. We can say in case of the two-dimensional case, we will get a hyperplane, and that is equivalent to our line. Okay? This is the equation of the line, the line equation. Okay, so that means for the case of our two-dimensional data points, we have to find out a separator line, line. So, that can be considered as a hyperplane, the equation of the hyperplane. So now consider that our two-dimensional data points, like here. This is the two-dimensional data point, and we want to find out the separator. Okay? So two-dimensional. This is the weight is given. It is given, and we want to find out the separator. The separator, as I already mentioned, that okay, maybe we can consider this one as the separator. Previously, we have considered this one. Okay, previously we have considered this one as the separator. And if we consider this one as separator, then support vector will be, this one will be one support vector, and this one will be another support vector. And this separator must be placed at the middle point between these two separator. Okay, between these two support vectors. Now, in the definition, I think we understand the support vector, we understand the hyperplane, because we have already derived the equation of generic form of a hyperplane. The rest, another thing is the margin. Okay, so we need to now understand the margin. What is margin? So here, the margin is the distance from this support vector to our hyperplane. So this is the distance from this one here. This is the distance. If we consider this one is our d1, and distance from this negative data point to the support vector, sorry, to our hyperplane is, this is d2. This is d2. As we can see, our separator we should place at the middle. It means that d1 equal d2. Okay, d1 equal d2, because the distance from this positive data point, let's say, if we consider that one is b, okay, c, it's a, this is b, and this is c. Then d, e, f. This one is d, this one is e, and this one is f. Okay, so from b to our separator, the distance is d1, and from e to the separator, the distance is d2. As we have to place the separator at the middle, so d1 equal d2. Okay? Now we can consider a garter that will pass to our b and parallel to our separator. Okay, so that means a garter. We can consider a garter is parallel to our separator, but it will pass to our data point b. Similarly, we have another support vector, that is e. We have to consider another garter here, and that garter, it will pass to our data point e and parallel to our separator. So maybe we can consider this is our another garter. Okay, another garter. Now the margin is the difference between these two garters, or we can say distance between these two garters. Okay, so this is called the margin. The margin here is, we can say, the rho. Okay, so this is the rho. So this is called the margin. Actually, it is 2 times of d1. Okay? 2 times of d1. So this one will be the margin. In our definition, it is mentioned the margin, and it is also mentioned that the margin is maximized. Okay? Margin is maximized. Why we need to maximize the margin? Okay, then at first there is what is the maximized margin? Okay, maximized margin. So let's say this is a separator. We can draw the separator in this way, and for this case, the margin is 2d1. Okay, 2d1. So can we build, or can we draw our separator, or we can say hyperplane, differently, so that we can get the margin that is greater than this margin, that is greater than this margin. So for that case, maybe you can consider, okay, maybe we can consider hyperplane. A hyperplane like this. So if we consider a hyperplane like this, on that case, what will be the support vectors for that? For that case, what will be the support vector? We can consider this the C, so this data point as the support vector, and this data point as the support vector. Okay, that is C and D. We can consider C and D as our support vector, because those are actually the closer to this hyperplane, closer to this hyperplane. Those are closer to this hyperplane. So now we need to find out the distance. Okay, so maybe you can say from C to our hyperplane, the distance is the F1, and D to our hyperplane, the distance is our F2, and again F1 must be F2, F1 equal to F2, F1 equal to F2, because we need to place the hyperplane at the middle between these two data points. Okay? So let's say this is F1, and if we consider now the garter, okay, garter of that, so the garter will be, maybe you can say, we can consider this one. The garter that will pass through the C, and another garter, there is this is positive garter, and negative garter we can consider. Okay, another garter is our this one. Okay. So this one is our another garter, and now we can see our margin will be this one. Okay, this one will be the margin, and we can see that is the previous margin. So this margin is smaller than this one. So that is, we can say there is the 2F1. This one is greater than 2D1. Okay, so the margin here, the second margin we completed for our second hyperplane. This one is greater than the first one. So that means we have to consider second hyperplane instead of the first one. Okay, so we need to find the second margin, that is the margin with greater margin, the margin with larger width. Okay, so we need to find out that kind of margin. Then why this one is necessary? What's the benefit for that? Okay, to discuss about the benefit, I think we can consider our data points again. Okay, so why we need to maximize the margin? Yeah, why we need to maximize? Okay. So let's say we have a hyperplane. This one is hyperplane. Okay? Hyperplane. We train our model, and finally we got this one hyperplane. And then for the test case, maybe you can see that one of the data point is here. This is A, one of the test case. So this is test case A. Another data point, maybe you can say here. This is B, the test case. Okay? And another data point is here. This is C. And this is our hyperplane. Above the hyperplane, those are our positive data points. After training, you can say above the hyperplane, those are our positive classes, and below the hyperplane, those are our negative classes. So positive classes and negative classes. Now, what we have to do, we can consider that, okay, what will be the class level of A? What will be the class level of A? as we can see that the point A is above our hyperplane. We can consider that this one is actually positive class. Okay, this one is, we can define that this one is positive class. For the test case, this is the test case from the test set. We can consider we can predict that this one is actually the A. Similarly, for the B again, you can see that this is also above the hyperplane. So this is also positive. This is also positive. And for the case of C, we can consider this is slightly above the hyperplane. Okay, slightly above the hyperplane. That's why we can consider this one is positive. Okay, this one is positive. But we can see that actually when we determine the class level of C, we have a lower confidence. Okay? This is slightly above the hyperplane. If we tilt the hyperplane a little bit, like if we can tilt the hyperplane a little bit, like if we can tilt it like this way, then we can see that the C is actually negative. Okay, C is negative. So that means confidence of determining the class level of C is lower than the A and B, because a little bit tilting of the hyperplane, it will not change the class level of A and B, but it will change the class level of C. So that's why we can say that is when we are defining or predicting the class level of A, we are more confident than when we define the class level of C. Why? Because the A is very far from our hyperplane. Okay, very far, you can say, very far from our hyperplane. So it is maybe if we tilt the hyperplane a little bit, it has no impact on it. So that's why we have more confidence. Okay. So that means the distance, if we can draw the hyperplane in such a way so that every data point will be in distant places or in larger distance, then that will be a better hyperplane. Okay, so if we can draw a hyperplane, for that case, every data point will be in greater distance. That kind of hyperplane will give us more confidence to say the data points, the class level of the data point. Okay, so that's why we are trying to maximize the margin. So maximize the margin. It means maximize the margin. It means for the maximized margin, the hyperplane and the data points, the distance of the data points will be higher. So that means we can define the class level of the data points more confident, in case of our that is the larger margin. Okay, in case of our hyperplane with larger margin. So that's why we are trying to find out the hyperplane with greater margin, larger margin, maximization margin. Okay, so we can see that's why it is mentioned that there is margin is maximized by the classifier. So now I think we understand a few concepts here. Okay, the concept of the support vector. So that means the definition here, the support vector definition. So we have already discussed about the concept of support vectors. We have already discussed about. I think we understand what are the support vectors. Okay? And then the hyperplane also, and the equation of the hyperplane already we derived it, the equation of the hyperplane. And then the margin we have discussed. Okay, the margin we have discussed the margin, and also we have discussed why we need to maximize the margin, and to define the margin we also see there is the how to draw the garter. Okay? How to draw the garter. Now the next thing is if we want to find the support vector, then we have to think about, like, we have to measure the distances. Okay? distances from each and every data point to our hyperplane. And then we have to find out the closer data points, and then we can define those are our support vectors. Those are our support vectors. Okay. So considering our previous data set, this was our data set. So if we want to determine the support vectors, so at first we can consider, okay, maybe we can draw a hyperplane like this way. Okay, this is our hyperplane. Actually, it's in a straight line. It's a straight line. So this is our hyperplane. Consider it, this one. So what we have to do from each and every data point, we have to find out the perpendicular distance. Okay, the perpendicular distance. So let's say this is A and this is B and this is C and D, E, and our F. Okay, so this is our data set. And now we want to find out the support vector. Then what we have to do? Have to find out the distance from each and every data point. That is, here A is a data point, and we need to find out the distance from A to our hyperplane, considering this one as a hyperplane, and B to our hyperplane. Okay? So that is B to our hyperplane, and C to our hyperplane. So we have to find out the distance. Similarly, D to our hyperplane, the distance. E from the E to our hyperplane, the distance. F to our hyperplane, that is the distance. So now we have to find out the distance, and then we will consider that is okay. If we want to find out the two support vectors, one from the above the hyperplane and one from below the hyperplane, then in this case we will get that is this one. There is the C. This one is our support vector, and E is our support vector. So these two will be considered as the support vector because the lowest distant data points. But how to find out the distance? How to find out the distance? So consider that this one is our line. So if we consider our equation of a line, so let's say, just assume that the equation of this hyperplane or this line, it is x minus, let's say, okay, x plus 3y minus of 4 equals 0. So this is the equation of a line. The equation of the hyperplane is a separator of two-dimensional data points. And we want to find out the distance from A. Okay, so A is a vector, or A is a data point. Let's say the height is, weight is 1 and height is 2. Then what will be the distance? So that means from this one, A, the perpendicular distance to our line. So I think most of you already know this from the high school math. There is from a point, the distance from a point to our line, the perpendicular distance, it will be, if this one is a line equation, and this is our data point. We want to find out the distance from this data point to this line. We have to replace the x utilizing the value of this vector. Okay? So that means x1 we have to place here 1, and then 3 times y. The value of y is, in this case we can see it is 2. Okay, so here is the 2, and then minus the 4, minus 4. As we are considering the distance, then we have to think about the absolute value. The absolute value, and then we have to divide it by the Euclidean norm. Yeah? So in this case, it will be a square root of. This is the equation. The norm of this equation. You can see x. The coefficient of x is 1. So here the 1 square plus the coefficient of y is 3. So here is the 3 square. 3 square. The distance will be on that case 3 times 2 6 plus 1 7 minus 4 is 3. 3 by the square root of 3 square is 9 and 1 is 10. So that is the square root of 10. This one will be the distance. Okay? So that will be the distance. So that means this distance will be 3 by the square root of 10. Similarly, we have to determine the distance from B, distance from C, distance from D, E, and F. Okay, we have to determine the distances. So for the two-dimensional case, we have this line, but we can say if we consider about the multi-dimensional, dimension 4, 5. So on that case, we have to think about the hyperplane equation. Okay, the equation of a hyperplane. Okay, then consider our hyperplane equation. How to find out the distance from a point or a vector to the plane. How to find out. And for that case, what we have to do, the hyperplane equation. So instead of our line equation, consider we have the hyperplane equation. The hyperplane equation is 8. Hyperplane equation. It's W transpose x plus b equals 0. If we consider our 4-dimensional data points, that means we have x1, x2, x3, x4, and we have w1, w2, w3, and w4. Okay, then what will be that distance? Maybe you can say a data point is A, and it has the vector values. Okay, it has, that is, if we consider our 4-dimensional data, that means we will get the 4 data points here. Let's say that vector is x0. Okay, that vector is x0, and we want to find out the distance from this data point from A to this hyperplane. And how to find out the distance? So distance of our hyperplane from a data point A, it will be, at first we need to replace this x utilizing the vector values of A. So on that case, what we will get? We will get actually W transpose x0. W transpose x0, and then plus, here is B. What we have to do, we have to find out the absolute value of that. Then we have to divide it by the Euclidean norm, norm of this hyperplane. Okay. So for that case, what we will get, the square root of in this W we have 4 components. So W1 square plus W2 square plus W3 square plus W4 square. Okay, considering 4 components. So 4 components. Then this one is called the Euclidean norm. Okay, Euclidean norm. Actually, the length of this norm, or of this vector. So we can write it like this way. So the numerator here is W transpose x0 plus b, so divide by the Euclidean norm is called also norm 2. So Euclidean norm of our W2. So 2 is norm 2. Norm 2 is the square root. Okay? Square root. So the distance from a data point A with the vector x0 to a hyperplane. So this is hyperplane W transpose x will be W transpose x0 plus b, the absolute value of that divided by the Euclidean norm. Okay, Euclidean norm. So this one will be the distance. So that means we have to determine, if we consider this is our this is the hyperplane equation, and then from A we have to find out the distance, from B we have to find out the distance, and from C we have to find out the distance. Okay? Distance. Then how to determine the support vectors? How to determine the support vectors? So that means for determining the support vectors, we have to find out the data points. The data points, those are closer to the hyperplane. So that means the distance, minimum distance, the data point with minimum distances. So we can say minimum distance. The distance we have calculated from each and every data point. If we have n data points total, the W transpose x, instead of x, we have to consider for each and every. So like the A has x0, so for each and every data points, we will consider the n. Okay? Like 0, 1, 2, 3, like this way. N plus of b divided by, just consider the norm 2. W2. Okay, norm 2. So this is minimization, but minimization over what? Minimization over n. So we have to find out the data point, that is the n, with minimum distances. So this is the minimum distances. So what we will get from here? We will get the support vector. Okay? We will get the support vector. Now, not only the support vectors, but what we have to do according to our support vector machine definition, we have to think about the margin also. Yeah. So the margin also, that means we need to maximize the margin. So maximize the margin, it means for the maximization, which element is responsible for the changing the orientation of our hyperplane. So like this is the line, how it will change. So if we change the slope of this line, then it will change. Okay, slope of this line, then the orientation will change. So that means we can draw maybe different lines. So this one, that one, and we can consider different lines. That one, even this one. Okay, so that one. So different lines we can draw. But for each and every line, we need to find out the margin, and the margin will be maximized based on what? Based on W. So that's why what we have to do, we have to now consider the maximization. So this is the minimization, the minimization, the minimization. But we have to think about also the maximization. Maximization. So this minimization, it will try to find out the support vectors, but we have to try to find out the margin that will maximize, and margin it will be based on the W. So that means we can say the W is there. So now we can consider this one is our argument maximization, ARG, argument maximization, where arguments are W and N. So maximization will provide us the maximum margin, but the minimization will provide us the support vectors. Okay, so we want to find out the support vectors. Those will maximize the margin. Okay, so for that, our equation will be this. This will be our equation for that. Okay, now we have to consider. Okay, so that means we have already considered two things. One is our support vector. So for support vector, we have to calculate the distance, and the minimum distance data point will be the support vectors. But at a time, we have to consider about the maximum margin. So that means for maximization of the margin, we need to change the W, and which W will provide us the maximum margin. We have to select those Ws. Okay, so now this is the problem. But one thing still we didn't consider, that is to draw our hyperplane. We need to consider that in one side the positive data points will be placed, and in another side the negative data points will be placed. Why? For the accuracy. Okay, in our training model, we have to place the hyperplane in such a way so that in one side all the positive data points will be placed, and in another side all the negative data points will be there. Okay, consider that. Okay, maybe if we consider up and down, so above the hyperplane we will consider the positive, and below the hyperplane we can consider maybe the negative data points. Okay, so as I already mentioned that, okay, considering these two things, the hyperplane can be drawn in such a way so that maybe in both of the side positive instances can be there. So that's why we have to think about now the accuracy. Okay, uh, to 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 determine the data points, to determine a support vector that will clearly classify the positives from the negatives. On that case, we need to consider about our there is the placement of our hyperplane in such a way so that maybe in one side the positive instances will lie and in another side the negative instances will be placed. Okay, so that's why that condition we need to add to this objective. Okay, to this objective. So now the next thing is if we think about how can we know that there is a data point is above the hyperplane or maybe the below the hyperplane. So let's say this is the hyperplane. This is the equation. Here it's hyperplane is actually the line equation. Okay, the line equation. If we consider that this line equation is x maybe plus 3y minus 4 is equal 0. Okay, so if a data point is maybe 1 and 1. Let's say a data point maybe A, and this is 1 and 2. 1 and 2. If we consider this data point 1 and 2, then if we put those values here, so it will be 1 plus 3y, so 3 times y is 6 minus 4. So that means it will return what? It will return 6 plus 1, 7 minus 4 is 3. So it will return 3. It will return 3. So this is the 3. 3 is greater than 3 is greater than 0. Okay, so greater than 0. If this one is greater than 0, okay, greater than 0, so not equal actually, it's equal. If this one is greater than 0, then we can say that that data point actually above our hyperplane, above this equation. Okay, if any of the data point we will get the negative. Okay, negative, then like -2, it means that the data point actually below this line. Okay, so we know this one from our high school math. So the same thing we want to apply. Okay, we want to apply here the same thing for the case of our hyperplane. So that is, we can see we have a hyperplane that is the W transpose x plus b, W transpose x plus b. So this is the hyperplane. And then a data point is A. And then if we consider that the vector for the data point is x0, and if we put it here like W transpose x0 plus b, if this data point, if this value is greater than 0, then it means it's above the hyperplane. So above the hyperplane, we consider that above the hyperplane, those are the positives. Okay? So those are the positives. And if we consider that this is W transpose x0 plus b, this is less than 0. So that means the data point is below the hyperplane. So below the hyperplane, we consider that those are our negative data points. Okay. So that means by checking this equation, W transpose x0 plus b, whether this one is positive or maybe negative, we can determine that, okay, whether the data point is above the hyperplane or below the hyperplane. Now, utilizing this, we want to determine the accuracy. So this is our separator hyperplane. Actually, it will provide us the class level, okay, class level. So for a test case, like if a point D is here, if the point D is here, and then this is our hyperplane equation. We put the value here in this hyperplane, and we got the positive. It means that D is above the hyperplane, so that means that D is also positive. Okay, so D is also positive. That means this hyperplane equation tell us that is what will be the predicted level. The predicted level of the data point. But from our data set, we also have the original class levels, because this is our supervised learning approach. We know the original class level of this data point D. Okay, of this data point D. So that means we can say D, we have the vectors here. Actually, in our data set, we will get the feature values and the class levels also. Feature values and class levels. So in a data set, usually we get that there is a feature value, like if we consider two-dimensional case, the width and height and the class level. In our data set, usually we get like this way. So maybe for the first instance, width is maybe 2, height is 1, class level is maybe negative, and then instance number 2, the 3 and 2 class level is positive, like this way. Okay, so this is the instance 1 or subject 1, but individual 1. So this is individual 1, and this is the data for the individual 2. So you can see individual 1 is negative. It means that individual has no obesity. This is positive. It means this individual has the obesity. Okay, and these are the values. These are called the feature vectors. Okay, feature values. So that means if we consider the first one, that is the first individual, then these values we can consider these are actually our x1. And x1 consists of two values, 2 and 1, this vector. And then this is our class level. Class level is, we can consider this is our y1. And y1 is, in this case, the negative. Y1 is negative. Similarly, for this is individual number 2. We can consider this is our x2. And the feature values are 3 and 2. And the corresponding y2 is positive. Okay? So here is the positive. So that means in our data set, we have not only the feature values, but also the class levels. The class levels are y and our feature values are x. Okay, so class levels are y. So now, and our W transpose x plus b, this is the equation of our hyperplane. So W transpose x plus b equals 0. Specifically, W transpose x plus b, if we put the value of any vector here, then it will tell us whether this one is positive or negative, like here. If we think about D, this one is our individual number 2, then if we consider 3 and 2 and place here W transpose x plus b, then it will predict class levels. Okay, so it will define the class level. So it will define the class level. Okay, now we want to find out an equation, and that can define our accuracy. So yn, and then we want to multiply yn times W transpose x and plus of b. Okay, these two things. W transpose xn plus b. If we consider n equal 1 at first, n equal 1. This is xn equal 1. And xn equal 1, it means 2 and 1. 2 and 1. So let's say this part of this equation, So let's say this part of this equation, it provides us some positive value. Okay, positive. And actually we can say y1 is what? Y1 is negative. Y1 is negative. So if we multiply this two, then what we will get? Negatives and positives. Whatever the positive, maybe positive 1, positive 2. Here is the negative 1. Then it will provide us the negative. Okay. Minus, here is the plus, that means negative. You can consider like negative 1, positive 3. If we multiply these two, then we will get the negative 3. Okay? So that is the negative. So actually, if we can closely look at this, so this is positive, this is predicted value, and this is original value. So originally, the class level is negative, but our model mentioned that this one is positive. So that means this is incorrect. This is misclassification. Okay? This is misclassification. So here we got the negative in that case. Similarly, if our model predict this one as the negative, and originally the class level is also negative. On that case, minus minus, that is, we will get the positive. We'll get the positive value. So that means the prediction and our original value are the same. Okay, so that means the positive. So this is correct. Correct. And this was incorrect. Misclassification. Incorrect. So incorrect. This one is correct. Misclassification. And this one is correct. Similarly, our model mentioned that this is positive, but original this one is also positive. Then this is also correct. And if we multiply these two, then plus and plus. If we multiply this one, then we will get the positive. So this one is also correct. So now, if we have the positive original, but actually model provide the negative, that means this is incorrect. So for the case of the incorrect, if we multiply these two, then we will get the negative result. So negative is there is incorrect. Incorrect. So that means for the case of the incorrect, we will get the value that is less than, you can say, less than 1. And for the case of our correct, when we have the accurate classification or accurately classify the instances, we will always get the positive results from this multiplication of these two terms. So that's why what actually we want to do, we want to find out the correct result. We want to find out the correct result. Okay, that means we want to, if we multiply these two, we want just positive value. We want just positive value. Positive means greater than or equal 1. Greater than or equal 1. Okay. So if it is 0, then actually it will be on the line. So that means we don't want that one. Okay, so that's why the greater than equal 1. So greater than equal 1. So you want this value greater than equal 1. So now we want to update our equation. So previously we have this one is our objective function. Now we want to update the equation a bit. How can we update this? So now we want to update it just by adding one new thing, because we have already W transpose xn plus b. Okay, xn plus b we have already this one, but we want to find out. Well, we want to multiply this one by ym by y. So here instead of our absolute value, we can consider W transpose xn plus b. Okay, and the previous equation, now we can see it will also consider this one the optimization function of three things. So it will determine the support vector by finding out the data points with minimum distances, and then it will try to maximize the margin by finding out the optimal value of W, and it will also try to find out the positive values. The positive values means the correct results, the correct classifications, utilizing the multiplication of yn and W transpose x plus b. So now this is actually our objective function. Okay, this is our objective function. This is our objective function. So now what we want to do, we want to write this one as a problem of optimization function. We want to write this one as a problem of optimization function, and how to find out that optimization functions figure. Okay. So in case of our optimization function, we have usually two things. One is called the objective function, and another one is called constraints. So we can write it using the argument maximization, argument max. Here is W, and 1 by this W2, and then such that the constraints, okay, the constraints you can see, you can write it yn W transpose xm plus b greater than equal 1. So this is now our optimization equation. Okay, so we want to maximize this 1 by W2 such that yn W transpose xn plus b is greater than 1. Okay, greater than 1. So this is our optimization function now. So now we want to simplify a little more. We want to simplify it a little more. So we can see that the first part here, this the objective function. This one is a maximization function of 1 by W2. So we want to make it a minimization problem. The same thing, but a minimization problem. So this is argument mean instead of max. We can consider argument mean. Argument mean of W of Euclidean norm W2 and such that Yn W transpose Xn plus B, and the value of this must be greater than equal. So that means the same problem we can consider about this from the maximization problem. We can convert it as a minimization, because we can see that maximization of 1 by x is, so one maximization of 1 by x is same as the minimization of x. So if we minimize the x, if we minimize the x, then it will maximize the 1 by x. Okay, so it's the same problem. Minimization of x is actually the maximization of 1 by x. So that's why we have here, that is the argument of W. So here is W. So Euclidean norm such that Yn W transpose Xn plus B is greater than equal 1. Now for quick convergence, or for some mathematical benefit, we also change this a little. So that means the argument minimization of this one. So we can add one new thing here. This is the half. So this half we have added here, and then the square is added there. Okay, so it will provide us the mathematical benefit. Just for the mathematical benefit, we have added the half and the square of that. Okay, square of that. So this is just only for the mathematical benefit. And for that, we can consider this is the equation. Okay, so this is our closed form solution of the problem. Okay, so that means our support vector machine problem. So this problem usually we call this one is support vector machine SVM with hard constraints. Hard constraints. So why hard constraints? Because we can see that we are strict here. Okay, we are strict. Here. That means it must be greater than equal 1. So what does it mean? It means that we actually don't allow any misclassification. We are not allowing any misclassification. That's why here you can see this is hard constraints. We are not allowing any misclassification. We can say this one always must be greater than 1. It means always we want the correct result. So that's why it is called the hard constraints. So no misclassification is allowed. So later we will see that is the how can we develop the same problem in using the soft constraint. That means we will allow few misclassifications there, and there are some benefit of that. So later we will see that. But at this stage, we can see this is actually SVM with hard constraint. SVM with hard constraint. So now how to solve it? Okay, how to solve it? Actually, we can see that what are the learning parameters. What's the target? Our target is to find out W transpose X plus B. So this is our target. That means we need to find out a separator line. We need to find out a hyperplane. Okay? Hyperplane, the equation of hyperplane. And in this equation, we can see W and B, those are unknown. Those are unknown. We need to find out the optimal values of W and B. So that's our target. But for that, we have to find out, we have to solve this optimization problem. And as this one is optimization problem, we can solve it using many optimizer. We can think about solving this one using the Adam, solving this one using the Saga, Newton's method, LBFGS, and then a Lagrangian method. Even we can find out the optimal field of W utilizing the gradient descent, or maybe the stochastic gradient descent. So now we want to solve this optimization problem using the Lagrangian method. Okay? So we will try to apply Lagrangian method to find out the optimal value of W1. Then how we can define, how we can solve this utilizing Lagrangian. To apply the Lagrangian, at first, what we have to do, we have to form the Lagrange equation. Usually we call it Lagrange multiplier equation. So a Lagrange multiplier equation, it means to form any problem, any optimization problem in Lagrange multiplier equation. So what usually we have to do, at first we have to write the objective function first. Okay, and then for each and every constants, we have to add a Lagrange multiplier. Usually we call it the alpha Lagrange multiplier, and then multiply this one with our constants. Okay, the constants, and these constants must be equality constants. Okay, equality constants. We have to transform the inequality constant to equality constant. Okay, so to write our Lagrange multiplier equation, Lagrange equation. Okay, so we can see that this one is actually our inequality constant. So this is inequality, not equal. Okay, inequality constant. To make it equal, what we can do, just we can transfer the one in this side. Okay, so in left side. Okay, so you can see, you can think about this one as so -1, and there is -1 equal 0 something. Yeah? So now it becomes the equality constants. So what we have to do now, we have to form the Lagrange equation. At first, the objective. What's our objective function? The objective function is argument mean. That means this part. Okay, we have to write half W. This is Euclidean now, the square, and then minus. Okay, then minus. For this one is y and w xn plus b. Okay, -1. So what we can do? So this is actually n. So that means many data points can be considered. Okay, yn and xn. So many data points. That means we can say only the support vectors can be considered here. Okay, because y and w transpose xn plus b. Actually, this one is only for the support vectors. Okay, support vectors. So that's why we can consider this as okay, alpha I, then the yi w transpose xi plus of b minus of 1 equal 0. So this is our Lagrange equation. Okay? Lagrange equation. Lagrange equation. So in this equation, we can see we have WB. Also, we have to determine the alpha. Okay, alpha. So this is alpha is called Lagrangian constant. Lagrangian constant. So now, to solve this optimization problem, we need to find out the value of the Lagrangian constant and then the value of W and B. W and B. So if we consider this equation as a the Lagrange equation, okay? Lagrange equation, and then what we have to do to solve it, at first we can take the derivative of this equation with respect to B at first, okay, with respect to B, and then with respect to W. So at first, take the derivative of this equation with respect to B. So what it will be L with respect to B, the partial derivative of L with respect to B. Then what will be the value for that? We are taking the derivative with respect to B, then W, on that case, it will be constant. Okay, so this part, we will get 0 minus, there is the alpha I. Then we can see here is the yi, w, and xi. All these will be 0 on that case because those are the constant with respect to B plus. And here is the B. Okay, B, that means we are taking the derivative with respect to B, that means it will be 1. It will be 1. And then this is minus 1. Okay, so minus 1 minus, we are taking derivative with respect to B, so it will be 0. Okay, with respect to 0. Is there anything wrong? Y WXI plus B. Okay, so that means okay. So W transpose XI, that means yeah, one mistake. So here is YN W transpose X plus B. So the parenthesis, we miss one parenthesis here. Another parenthesis we have to put here. W transpose X plus B, then this is YI, and then the negative one. Okay, so that means like this way. For that case, this is yi w transpose xi, here is the b. So that means when we are taking the derivative with respect to b, it will be 1. But here is the yi. So we will get 1 times yi. So yi times 1. And this yi actually we can see we have to consider for all cases. So that's why we have to add summation there. Yeah, because not only the one single data point, we have to consider for all the support vectors. Okay? So support vector can be multiple. That's 2 support vectors at least. So that's why the I you have to sum up. Yes, that's why here is the summation of I. Then we can see from here it will be alpha I yi. Okay, so negative of summation of I, alpha I and yi. So to solve this equation, we have to put this one equal to 0. Okay, this one equal to 0. So it means summation of I, alpha I, yi equal to 0. So this is one of the equation. Okay, this is one of the equation. So this is the first equation we got from the Lagrange equation. The Lagrange equation. The first equation is this. Now what we have to do, we have to take the derivative of our Lagrangian equation again with respect to W. With respect to W. If we take, this is the equation, and we want to take the derivative of this equation with respect to W. It will be delta L with respect to W. On that case, we can see half, and here is W squared. So the half is there. We are taking the derivative with respect to W. So W squared, so 2W. Okay, so we will consider here 2W. And then minus, you can see here alpha I, the summation of I, here is alpha I. Then we have to think about the, here is the yi, that is the W. So yi is there. We are taking the derivative with respect to W. Here is the W. So xi, so we can see xi times 1 times 1. And plus of, this is the B. We are taking the derivative with respect to W. So B is constant on that case. So it will be 0. It will be 0. And the negative, here is negative 1. So negative 1, we are taking derivative with respect to W. So it will also be 0. Okay, so it will also be 0. Okay. So this one will be the case if we want to take the derivative with respect to W. Then it means we will get, here is the 2 and half cancelled out. As I already mentioned that the half is taken for the mathematical benefit, and we can see that actually this is the mathematical benefit. We can cancel it out so that maybe there is no need of the square root, or we can say no need of the multiplication. So now here is the W minus alpha I yi xi. Okay, it means what we will get, there is alpha I, is yi and xi. Okay, so that means it will be summation of I, alpha I, then yi, then xi. Okay, so now to solve it, put the value of dl dw equals 0. Okay, so it means we will get here the w equal summation of I, alpha I, yi, xi. Okay, so that means this is the second equation we got from our Lagrange method. Now what we have to do, we want to update our equations based on these two things, okay, two equations. And another thing, sometimes you will see that the xi here, this xi, this is the direct feature values, okay, this is the direct feature value because feature factor is x. Sometimes we need to translate, or we can say we need to transform this x to a new feature vector, okay, new feature vector. Specifically, if we have like linear, that is the data points, to make it the linear form so that we can apply the linear support vector machine, we need to transform those data points. So that's why you will find that this equation sometimes we can write it as this is I, so alpha I, yi, and instead of just xi, the transformation function phi and xi. Okay, so in some of the cases you will find this equation, okay, this equation. So that means after transformation of the x, okay, so w equal this summation of alpha I, yi, xi. Now based on these two equations, equation number 1 is summation of alpha I, yi equals 0, and w equal summation of alpha I, yi, and xi. Utilizing these two equations, we can derive some other equations also, okay? Some other equations, specifically by replacing the value of w. So what are those equations? I think it's better if we can directly show you from our lecture slide. Okay. So we can see the equation number 3, the decision boundary. Okay, decision boundary actually, what's it? It is our W transpose X plus B. Okay, so that is our decision boundary. W transpose X plus B, the decision boundary, and its value must be greater than 1. Right? Here it is mentioned greater than 0. Okay. So this is the decision boundary. Change the value of W here, because we know W equals summation of Wi, yi, and xi. So here is instead of just W, we can put this summation of alpha I, yi, and xi. Okay. So then this equation will be this. So the hyperplane equation will be this one. And as we can see, that is the xi and x. We can rewrite is utilizing the kernel function. We can say kind of the multiplication, or we can say transformation. Here is the xi and x. Here is the xi and x plus b. Okay, so we can rewrite it like this way. Similarly, the positive garter. So we can say that is W transpose X plus B equal 1. So this is the garter passing through our positive data point. So we can write it W transpose X plus B. So again, the W can be changed like this way. So alpha I, y, and xi. Okay. So similarly, we can write it using the kernel function. The negative garter is -1. Okay. So the negative our negative data point. Negative support vectors. So that equation is this one, and again we can change the W here. Okay, so the equation will be this, like this. And also we can determine the width of the margin. The margin is, we can see that is our 1 by W, and we know that that is the twice of that. Okay, so the margin is twice of that, 2d1. Okay, so d1 is 1 by W here, where the W is square root of the summation of this. Okay, so that is Euclidean norm. So we can find out that is here the W, and the W is alpha I, yi, and xi. Okay, so we can determine the M. Okay, we determine the margin, the width of the margin utilizing this equation. So now we can see we have total 6 equations here. 2 equations directly from our Lagrangian equation, by taking the derivative with respect to d and w and other equations. We can utilize those values in those equations to find out the new form of those equations. Okay, so these are the equations now. So now utilizing those equations, we can solve any problem. That is the support vector machine problem for any data set. Specifically considering that the data points are, or the problem is linear problem, or we can solve it utilizing the linear support vector machine. So there are several examples here. I think I will explain this example in next class. Okay, this example, there are several examples. We will discuss this example in next class, utilizing those equations. And also I will discuss about the nonlinear support vector machine in our next class. So thank you for joining this session. See you in our next class. So do you have any question, queries?
No, sir.
If you don't have, hello.
No, sir.
হ্যাঁ শুনতে পাচ্ছি, বলেন।
স্যার কোনো কোশ্চেন নাই, এটা বললাম স্যার।
Okay, thank you very much. Okay, I will announce some of the announcements in our Google Classroom. Please check the Google Classroom so that you can get the announcement. Okay, thank you.
Thank you, sir.
Okay, thank you.